Hey everyone, it's John, and today what I want to do is do a video on VXLAN. Now, before I start, what I will say is that VXLAN comes in kind of two flavours. The first is data plane learning, and the second is control plane learning. Now, control plane learning is a little bit more complicated, and I'm going to do that in a later video. What control plane learning is for larger implementations of VXLAN, especially in, like, say, hyperscale environments like a Facebook data center or whatnot. Basically what it uses is multi-protocol BGP, and it uses that to carry the VXLAN information and MAC addresses dynamically across different switches. Now you're going to see that this is very different in the data plane learning. We're going to be a lot more manual with it, and that's why it doesn't scale well on the larger level. But for the initial implementation, data plane learning is quite simple to learn, so I'm going to show you that one first. The second thing which I want to talk about is I'm actually going to be using Arista switches. The reason for that is because your ordinary viral images do not support VXLAN. You need to use the Nexus switches, and now whilst I do have that because of my viral account, each switch requires about 8 gig of RAM. So if you can imagine this topology here, we'd have 8, 16, all the way right up. It's just going to get crazy and my computer's just going to blow up basically. So in the future video where I'm going to demonstrate it on the Cisco switches on the Nexus devices, I'll be using a cloud implementation which has got high specs, like maybe say like 128 gigabytes of RAM. So this one's going to be using Arista, but what I'm going to say is, see, you'll notice actually, see the Arista operating system, it's so similar to Cisco. You wouldn't have EIGRP or maybe CDP, but see the commands, show run, your show version, show IP interface brief, is all the same, but in this case the VXLAN configuration actually is a little bit different, so just be aware of that. Another thing which I want to talk about is this topology here, because this video I don't want to go into too much detail because I'm trying to get towards the configuration more. I noticed that when my videos are shorter, people tend to watch them more, so I don't want to be rambling too much. That tells me that you prefer the shorter videos. So I just want to give you a little bit of context. I don't like getting into a video just blind and just showing you configurations and there's no kind of context as to why we're doing it and how it works. I just feel it lacks a little bit for me. So I'm going to explain this topology. So basically, you will be used to seeing a topology which looks like this. And this does work in data centers still. The thing is, and for reasons which I'll explain, it's just a bit suboptimal in terms of design for performance, and we'll just demonstrate that quickly. So you can probably see what I'm doing here already. This is the core layer. This is the distribution layer. And this is the access layer. Now we have our connections from distro to core, up. Forgive my lack of artistic abilities here, a little bit messy. But you know the drill, just to show you the basic implementation. And across here we go. And across here. And here. Right. So this is a basic topology, and if we had a server here, and maybe a server here, and perhaps another server here. Now here's the thing is, see, in data centers you tend to have what's called an east-west traffic flow, because servers actually need to talk to each other. You've got an application server talking to a database server, talking to a web server, all these types of things. So in the case of this, the traffic path from this to go to here is just fine. It goes bop, bop, 1, 2, all good. But if this one wants to talk to this one, the traffic path has got to go what's called northbound, right? So it's got to go here and all the way up to here to traverse a path across here and down here. So we've got 1, 2, 3, 4. Now, whilst that might not seem like a big deal, when you're dealing with data centers, performance is everything, so you really want to have high performance. So the reason why this design was scrapped was because we could do it better. And the way you could do it better was by devising what's called a spine leaf topology. Now it looks kind of similar, it's hierarchical. You've got this layer up the top called the spine layer, and below it you've got the leaf layer. But the main thing is that we have two spines in this case, and the spines do not connect to each other. No connection here, okay? Every connection is between a spine and a leaf, so every leaf connects to every spine. So you've got this crazy mesh. So if you've got all these devices, it's just everything meshes with each other, okay? So if you add in more leaves, you get more availability. You can plug in more servers, and if you add in more spines, you get more bandwidth because every spine will connect to every single leaf. And this just goes and goes and goes. So whilst it looks kind of messy in terms of visually with the links all crossing, this is actually designed for that traffic path. So the reason why is, again, if we draw the same scenario out, we've got a server here, and a server here, and a server here. Now if this server wants to talk to this, it just goes 1, 2. If this server wants to talk all the way over here, it's still 1, 2. In fact, any point in the network is always going to be 2 hops away effectively, no matter where you're going from, whatever switch to whatever switch. And all of these links are high performance, high bandwidth. You could have, say, 10 gig, 40 gig, or maybe even 100 gig, okay? And we're just going 2 hops, 2 hops. So that's the whole point of having spine leaf. And the thing is as well is that all of these links, this is important here, all of these links are layer 3. Now, why would you not use layer 2? Well, I've written down some problems here with layer 2. Like I say, having a large layer 2 domain isn't good design. The larger the layer 2 domain, the larger the broadcast domain and failure domain. So if you've got an errant switch throwing out lots of broadcasts, you could potentially take down a huge chunk of the network because the broadcasts are traversing right across the network, okay, because of the layer 2 domain is large. So another key thing, and this is really is key for the data center, is that with layer 2, how do we prevent loops? Prevent loops using spanning tree protocol, which does what? It blocks links, okay? So if we've got this high performance network and we've paid, say this example, this link here is 100 gigs, do you really want it sitting idle? Do you really want it sitting unused because it's been blocked by spanning tree to prevent a loop? Think of all the wasted bandwidth, think of all the wasted performance that causes. You really want, especially in a case like a data center where performance is key, you're basically fighting for every millisecond. You want all of these links to be firing out data, all of these links being utilized. So the reason we get rid of spanning tree is so we can actually have all these links forwarding. So because of that, we want layer 3 everywhere. And another advantage, which I've written with layer 3, is obviously you've got all links forwarding, and the broadcast and the failure domains are severely limited. So if you happen to have an errant switch, the problem tends to be localized to a single switch and therefore a single network. This would be one here, rather than this switch going mad and breaking the whole network, or maybe not causing an outage, but really bringing performance across all of the switches down to a sluggish rate. If this switch is underperforming and it's layer 3, it's just going to tend to knock out this switch. Another thing is with routing protocols, i.e. if you run OSPF over here or ISIS or something like that, or BGP, you can get, well, particularly with the IGPs, automatically you're going to have intelligent load balancing across multiple paths, and that's what we're going to be using. We're going to be using our full bandwidth, and we're going to have that rapid ECMP failover. So if this link fails, we just get the rapid, we just go this direction. So if this one breaks, we go this way. This one breaks, ECMP goes this way, and we've still got that rapid connectivity. So the thing is, clearly, layer 3 is a big, good thing. That gets a nice green tick. So what's the problem here? Layer 3, it sounds great, you've sold me on it already. The problem is that with, particularly in this current era of virtualization and containers, a lot of these virtual machines need to have layer 2 adjacencies. Say for example you wanted to migrate a VM from this here over to here. By doing that, if they're on different networks, you're going to have to change the IP address, the subnet, everyone's got to change, okay? You can't just clone it over here. Like I say, also with typical implementations, you've got VMs, and you've got, like, say, a web server spun up VM here, and maybe a database server here, and just a basic application server. And the traffic path, like I say, in data centers are not so much northbound facing, going towards out to the internet. It's actually all these servers talking to each other, having a big chat, and a lot of time you need layer 2. So if layer 2 terminates here, and here, and here, and here, and here, and here, and here, because of the layer 3 links, how are we going to have this layer 2 adjacency connected over here? The answer to that problem is in this video. It's something called VXLAN. Now what VXLAN does in a very basic form is, if you've got a frame here, and in here you've got your IP packet, what VXLAN does, it actually re-encapsulates it again, and we've got some VXLAN information, and it's all encapsulated within UDP, which adds low overhead. So what we're really doing here is we're using an encapsulation method to encapsulate our layer 2 stuff here, and we're going to shoot it over an IP layer 3 network and then unwrap it at the end of the tunnel point, and then it becomes layer 2. So effectively what it looks like is that in the case of, if we've got this server talking to this server over, oh, keep touching that button there, over this IP network here, the logical implementation, the way it actually communicates, it's like you've got a server and a server with a switch just talking, and it's all layer 2. Even though we're getting all this ECMP and no spanning tree, it's transported over IP, but the logical way they're talking is still L2. So that's why we want VXLAN. Another reason is because, especially in hyperscale environments, like I say, in Microsoft data centers and Facebook data centers, Google data centers, what you want is a lot of logical segmentation. And the reality is, the amount of VLANs which we have, 4096, just does not cut it in those scales. So with VXLAN, what you actually get is you actually get this extension. Because of the packets enlarged, we get more bytes to play with, and we actually now get 16 million identifiers which can identify, and this is what I want to talk about. These are called VNIs, and these are what we're going to group together to denote that they're the same VLAN. So if we have a VNI here, VLAN 3000, which is going to be for our VLAN 3 here, and VNI 3000 here, that tells VXLAN that these are the same VLAN. The way I think about it is VNI, I think for the same VLAN, they have to be VN identical. Okay, so 3000, 3000, that tells you they're on the same VLAN. These other things are called VTEPs. These are the tunnel endpoints, and in this case, by using flood and learn, this is what it's called, the data plane learning, the implementation we're doing, we actually need to specify manually where the tunnel endpoint is. So for example, in the case of this one here, we're going to tell this switch that we've got a VNI of 5000. This switch is going to be told this has got a VNI of 5000, and to associate that with VLAN 5. Okay. Now, in this case here, we're going to tell the switch when we have a frame come in, which is VLAN 5, I want you to encapsulate it in VXLAN with VNI 5000, and we're going to tell it where to send it, because we don't want to just flood it out everywhere. That's not what we want. We want to target exactly where we want to tunnel that VXLAN traffic to. So in the case of VLAN 5, it's on switch 6, which has got a loopback of 6.6.6.6, and the endpoint of that is going to this switch, not this switch here or this switch. We're going to this switch because this is where this one's attached to, VLAN 5, VLAN 5. So what we do is we tell it the VTEP target address is effectively 3333. Okay, in the case of this one here, we're going to say VNI 3000. If we're going to associate it, we're going to route that to VTEP 3333. This one here, we're going to say we are stretching VLANs to VTEPs 6666 and 7777. We've got two here we've got to go. So we're not flooding it to every device. That's why I've left 2 here. This could be a much larger topology, obviously. And we just say particularly, we've got a whole big VLAN 3 here, but we've just got a server here we want to stretch it to. We just say, listen, we want to stretch that just to this tunnel endpoint here. In case of VLAN 5, we just want to just stretch it not to 4 or 5, but just to 3, because that's what our other VLAN has been stretched to. Now this might be a little abstract at first, like I say, a lot of this stuff you kind of have to see in practice, and that's what we're going to do just now. So what I'll do is, I'll kick on and start the configurations with that little kind of preamble, just because I like to, just so you've got a reason why you're doing this, and kind of can see what makes sense. So the first thing what I'm going to say is that we've actually got, these links here are all point to point, they're basically /30s, like 10.0.0.1, 10.0.0.2, 10.0.0.5, 10.0.0.6, so on and so forth, okay? So they're all just point to point /30s, all no switch ported. So they're all layer 3 links. What we're going to do is run all of these in OSPF area 0, okay, to start. So let's go and do that just now. And what I want you to notice as well is, like I say, see with this here, I was just demoing this before I started, so I'll just make sure I remove this. Just before I start, like I say, I'm using Arista, but just look how similar the commands are. You do a show run, you get your show run configuration, a show IP int brief, a show version. It's all really similar, do you know what I mean? Configure terminal. It's so similar. So don't be too wary of trying out something different if you're not used to this. But what I will say is the VXLAN in particular is actually a little bit different. So whilst this is good to play with, be careful, these commands exactly won't work out on Cisco switches, and I'll get to that when I use the more high performance cloud environment to demonstrate the Nexus. But let's kick on and do it then. So we'll do router OSPF. Actually, do you know what? We'll do IP routing first, and we'll do router OSPF, and we'll do show IP routes include the connected, and we'll do net 1111 area 0, network 10.10.10.0 and 3, just up arrow, make that 4, make that 8, make that 12, and 16. Right, that should be the spine one done. Let's do spine 2. And configure terminal IP routing router OSPF 1, do show IP route include connected, and we'll do network all the 2s. Oh, have I still got that there? Like I say, I demoed this just quickly before I recorded the video. So I'll do net and net 20, up arrow 24, up arrow 28, 32 and 36. Okay, now let's go and do our leaf switches. Start with number 3. IP routing, router OSPF 1, network all the 3s, network, to show IP OSPF neighbor, and that's us in two-way state. IP routing router OSPF 1, do show IP route net all the 4s, up arrow 32. Let's go into number 5. Router OSPF 1, and do show IP route include connected net all the 5s, and we'll do 28. Okay, let's leave 5, let's do leave 6. IP routing, I think I still had, make sure I've not got OSPF in this one, and do show IP route, and we'll do net all the 6s. And the last one is up arrow, okay, we're in init stage. Okay, so what I'll do is if we just do a show IP route, you can see we've got our connectivity across this, which is just fine. So all we've done is just basically run OSPF here. Now we're going to do is create our VLANs on these devices. And you'll notice, like I say, super similar to Cisco. Just call it name3 because I'm dead creative. And just call this one name5. So we do a show VLAN. That's our VLANs there. And on this one, and by the way, like I say, I've left these ones idle. You can imagine these could have lots of VLANs connected to them, but in the case of these ones, these are the only ones which we're actually stretching across layer 3, so that's why I'm just leaving them. So let's go here and do VLAN 5, name 5, and this one here is VLAN 3, name 3. Okay, so now what we're going to do is configure our VXLAN. So we'll start from the right hand side at first. So what I'm going to do is do interface VXLAN and give it a number 1 VXLAN. And what we're going to do is do our source interface. Now our source interface is going to be loopback 0, which is all the 7s. Okay, 7777 is our loopback 0. And we're going to say VLAN, and this is basically associating, big caps lock on there, associate the VLAN with the VNI. So what we want to do is say we are VLAN 3, our VLAN 3, when you get a frame with VLAN 3, I want you to use VXLAN to give it the tag of VNI, in this case 3000. So if another switch with VXLAN configured sees 3000, it knows that it's the same VLAN, okay? So when we get a VLAN 3 frame, make it VNI 3000 and route it across. We also need to say is VXLAN, and we're going to say flood, and this is the data plane there that I'm talking about. This is the manual part. We're saying VTEP. Where do we want to flood this to? VLAN 3, do we want to flood it to 6? No, because VLAN 3 is not there. Do we want to flood it to 5? Definitely not. 4? Definitely not. No. We've got a second VLAN across here, so we want to flood VLAN 3 with VNI 3000 over to switch 3, because that's also got VLAN 3 VNI 3000. So just specify the address, so we're going to 3333, and that's it. Now we're going to go and do the same thing here. So we'll do interface VXLAN 1 VXLAN, and so I'll keep hitting caps lock. Source interface is loopback 0, which is all the 6s. I'm going to do VXLAN VLAN 5 VNI 5000. So that basically means if you get a frame with VLAN 5, wrap it in VXLAN and put the tag 5000 on it. VXLAN, and we're going to flood that again. Where are we going to flood? What tunnel endpoint do we want? 5. Well, 5 has also got a tunnel endpoint associated with this switch here, because we get VLAN 5 here, VLAN 5 here, so we want to flood that just to this switch, and the tunnel endpoint address in this one is 3333. So let's go and do that. So VTEP, where is the remote VTEP? It's 3333, and that's that done. Now the last one here is a little bit different because we've got two configurations, but it's still pretty similar. We just go in and do interface VXLAN 1, and we do VXLAN source interface loopback 0, VXLAN, VLAN. We want to associate VLAN 3 with VNI 3000, but we also want to associate VLAN 5 with VNI 5000. So we just did two commands there. And we also want to do VXLAN, and we're going to send our VXLAN floods to two different VTEPs, okay? Because this switch is going to have two targets, so it's going to target this switch, and it's also going to target this switch because it's got two of these, okay? So this one's got to go to 6, this one we're going to target 7, so we're going to flood to these two different ones. So VTEP 6666, that's the first one, and the second one is 7777. And that's it. So let's go and put our switch ports in. So in this case we Ethernet 7. I'm going to put that into VLAN 3 in ETH 7, and we are going to do switch port mode access. Again, this is just so Cisco like. Access VLAN 3. And let's go over to this one. We'll do in ETH 7, switch port mode access, switch port access VLAN 3. Okay, so let's just see, we've got this IP network over OSPF, and we've got this subnet divided over this IP network. So let's put an IP address in this 192.168.3.2 and give it a /24. Yep, /24. And we'll also make this one 3.1. So IP 192.168.3.1 /24. And what we'll do is we'll ping our own address first. And you see that? We've got reachability right across this IP network. We don't even have a default gateway configured. All we're doing is we're sending that to VLAN 3. This is tagged to VLAN 3. VXLAN knows, okay, we've got a VLAN 3 frame. I have to wrap that in VNI 3000, and I route it to these endpoints. So I route it to bang, bang. This one doesn't understand it, so it's just dropped. This one here does understand it. It goes, I've got VNI 3000, I'll unwrap it and we act like a frame again. So now we're just talking pure layer 2, even though we've got a layer 3 connection. Does that make sense? Okay. So we'll do the same thing here. We'll also put Ethernet int ETH 8 switch port mode access, switch port access VLAN 5 this time. And we'll do an ETH 7 switch port mode access, switch port access VLAN 5. And let's do the same thing here. We'll make this 5.1. So IP 192.168.5.1/24. And make this 5.2. IP 192.168.5.2/24. (5.2), and we've got connectivity. Now here's the thing though, if we want to route out to our different VLANs, you notice we can't actually do that. Like I can't ping. Okay, we've got no gateway configured, so what I'm going to do is configure a gateway on this. So in this case of we've got interface VLAN 3, and what we're going to do is we'll make the IP address the last one, so 192.168. Actually, it's not just that. What you need is put a virtual address on. It's not just an IP address, because we're going to actually have the same address across both switches. You'll notice this. So 168.3.254. Okay, so that's the address here for VLAN 3. IP address virtual, remember that part. And for int VLAN 5, we're going to do IP address virtual 192.168.5.254, give it a /24 mask and no shutter. And same here. And VLAN 5, IP address 192.168.5. Oh, I'm forgetting more advice here. 168.5.254. And we'll do int VLAN 3, IP address virtual 192.168.3.254. And what we'll also do is we'll put this into OSPF. And 192.168.5.0. Router net 192.168.3.0. Okay. So now what I'll do is I'll need to put the actual gateways on these PCs as well because they've not been configured with a gateway. So I'll do IP 192.168.3.2/24, but we're also going to give it a gateway of 3.254. Okay. See, we've got no gateway here, so let's give it that gateway. IP 192.168.5.2/24, and we're also going to give it the gateway of 254. And we'll do IP 192.168.5.1/24 and (3.1/24) 192.168.3.254. So let's try and ping these gateways first. Okay, that gateway's fine. Close this. That's fine. That's fine. And last one. Okay, so we are on this one here, so let's see, we can ping 192.168.3.1, which is across. This is this one here. Now let's see if we can also ping 5.1, which we can as well. So now we can route across all of them, and we can also stretch our layer 2 across this IP layer 3 network. So that's the purpose of VXLAN. So like I say, this video is just on the data plane learning version. The next one I'm going to be doing is MPBGP VXLAN with EVPN, which is the version to scale, so you don't need to keep specifying this VNI goes to this VTEP and whatnot. It's all done dynamically through BGP. So that's the end of the video. Thanks very much, and I'll see you guys soon. Bye bye.